Welcome to our webinar about commercial domestic hot water heating systems. It will be a two-part, as Miranda said. First, we'll do the PDH accredited presentation, and then we'll do also a short presentation about the Vitotrans 300, our new water heating package. So a couple of housekeeping slides before we start. Here's the information about copyrighted materials. Again, if you would like a copy of this, we can provide you a copy in PDF format. Here's the information on our accreditation for the PDH. And let's talk about learning objectives. Learning objectives are all about the PDH portion, and then we'll follow up with the Vitotrans portion afterwards. So during this session, we're going to list the information required to size a water heating system, including the differences in various methods. We also will explain how to size a domestic water heating system using the common methods. And what I'm going to use as common methods are some of the methods that's outlined in the ASHRAE manual. Once we look at sizing, we'll kind of contrast the various water heating methods because there's a lot of ways to approach water heating. All of them have their strong points. So we'll kind of look at each one of them, see where they really shine from that application standpoint. And then if we are looking at the aspect of using a space heating boiler or for the heat source in an indirect type system, we're going to look at a couple of ways of maximizing performance for indirect water heating systems, which is a fairly common question that we get when we're looking at doing domestic hot water. As Miranda said, if you have any questions as you go along, please type them in, and we'll cover the questions as we work our way through. So with that, let's talk about water heating, okay? And water heating's interesting for a lot of people that do size water heating systems, but also deal in the boiler world. Typically in the boiler world, it's pretty straightforward in sizing things. In water heating, it's interesting in that there's a lot of different approaches to a domestic hot water application, okay? Now, what drives a lot of the different approaches is the water heating solution could be a combination of storage and recovery. Water held in a tank ready for use, hot, that we draw against, or recovery, we generate the hot water as it's being used, or somewhere in between. So the challenge is, how do I approach it? Do I go with a high level of recovery, let's call it an on-demand system with no storage, or do I go to a high level of storage? The challenge with a high level of storage system is always recharging the system. And the fact that when I look at storage, I also have to define the demand period, because with storage, once the storage is gone, now I'm back down to just recovery. But in most cases, we're going to see some combination, somewhere in between the extremes. And where almost the grayness comes into play is how much storage versus how much recovery am I really looking for, okay? Now, the other thing that changes is when I look at the method of generating or providing the hot water, a lot of times the method has to change. If I'm going to go to an all demand or an all recovery system, then I have to size with a procedure that will give me a full recovery number and no storage whatsoever, okay? Now, with the two styles of water heaters, and this is going to be part of the discussion when we start to talk about the various methods. There is always challenges with each type. So, the minute somebody starts to talk about storage commercially, all of a sudden I may be thinking about 500 or 1,000 or 1,500 gallons of stored hot water. Those tanks of hot water have to go someplace. It becomes a footprint issue. Whereas if I say, I'm going to go recovery, I'm going to go on demand with my system, now it's all about the characteristics of the heat source. I have to make sure that I can generate enough hot water to keep up with the peak demand period. But then comes the flip side, the low flow situations. I have to make sure that I have the ability to provide a low enough flow rate to adequately take care of the low flow situations, including hot water recirculation. So those are always discussions above and beyond just sizing for water heating, okay? Now, there's a lot of locations or a lot of different methods or places you can go to find out information on water heating. The one that I tend to go to the most is the ASHRAE handbook. It has a series of methods of sizing water heaters, and we will work our way through those methods. ASPE, the American Society of Plumbing Engineers, also has information on water heating sizing. Their information pretty much mirrors what ASHRAE puts out as well. A fairly popular method is going to a manufacturer to size it for you. Most manufacturers will either have some sort of paper format for sizing water heaters, or they may have, a lot of them have something on their website where you can go in there, input the information, and from that information, it will size a domestic hot water heating plant for you. Another one that comes up when we start to look at water heating sizing is codes. A lot of times a municipality will actually outline how the water heater has to be sized within their jurisdiction. And then the final one is self-generated methods. You know, a lot of times people will look at the various methods, particularly stuff that's in the ASHRAE manual, and say, you know what, I want to put my own sheet together. And a lot of times it may follow directly out of ASHRAE or ASPE. Sometimes somebody puts their own little spin of almost a safety factor in there as well. So there's a lot of information and a lot of different approaches to sizing for domestic hot water. Today, we're going to concentrate on the methods that are outlined in the ASHRAE manual. One of the other things about water heating sizing is if you look at all the methodology that's out there, none of them ever agree on what the numbers are going to be. So if you're either looking to help for water heating sizing from someone else, or somebody's, you know, would like to help you with it, ensure that both of you understand the approach that's going to be taken for water heating sizing. You know, that way there, the final results meets everybody's expectations. So with that, we'll take a look through. Now, probably the easiest way to do this and to explain the methods is to actually size an application. So throughout working through the methods, we're going to size an apartment building. Okay. So for our presentation, we're going to size an apartment building. The apartment building is going to have 150 units. All apartments are 2 to 3 bedrooms with 2 full baths. The kitchens include dishwashers, and there are no clothes washers in the units or in the building. Now, with domestic hot water sizing, one of the things that I need to know is what information is necessary. You know, I often have guys will call in and ask me to help them size a water heating system with not enough information, and we end up going back and forth to pick up that information. So over here, I actually have most of the stuff I'm looking for. It's going to be an apartment, so I know what kind of, where I have to look in the information to size. I'm sizing an apartment. It has 150 units. That's pretty much a standard piece of, these 2 pieces of information are pretty much important information regardless of how I'm sizing for hot water. Now, some of the methods actually work off the fixtures in either a gallons per minute, gallons per hour, or we'll call it a fixture unit basis. So it's important to know what's in each apartment for fixtures. So they're all 2 to 3 bedroom apartments, 2 full baths, kitchen including a dishwasher. That's telling me in each apartment there's going to be 2 private labs that I have to account for. There's going to be 2 shower tub combos. There's also going to be a kitchen sink, and there's also going to be a dishwasher. Now with this, I think for most methods, I have pretty much all the information I need. There is one exception. It's called the occupancy type. We'll talk about that later on. With that, I also need to know the occupancy type. The easy ways are, is it a couple? Is it a family? Is it a big family? Really are kind of almost the dividing lines for this. But we'll talk about that when we get to that individual methodology. So with this, let's kind of start looking at where we need to be from sizing. Okay, method 1, directly out of ASHRAE, you'll notice a lot of my graphs and figures that show up, but they're snapshots out of it. It's one of my ready reference. So this I'm going to refer to as the recovery versus storage or a draw profile. In the ASHRAE manual, you'll find that there is a series of figures. There's about, I think there's 8 or 9 of them that deal with specific applications. So that's why it's important to know the application. This one happens to be for an apartment. There's a motel, there's restaurants, there's schools, there's dormitories. You know, so you have the chart for the specific application. It's based on historical information. And with this method, all of the other data doesn't matter. You know, it doesn't, you know, there's nothing in there that I go in there and account for the fixtures. It simply is looking at a specific application. Now you'll notice in there with this method for a lot of the charts, there's going to be multiple curves. For the apartment building, there's 20 or fewer apartments, 50, 75, 100, or 130 more apartments. Okay. And with these curves, across the bottom of this scale is usable storage capacity, gallons per apartment. Okay. The vertical is recovery capacity, gallons per hour per apartment. So it's in all the methods, those are the two things we're looking at, how much storage and how much recovery. With this method, it's a little bit different than the rest. Most of them, you enter your data and the methodology will tell you the recovery and the storage. With this, you have to decide on a storage or decide on a recovery, enter the graph, and then calculate the other piece of information. Okay. Now, among the methods, the methods, typically what I find is this tends to have the smallest domestic hot water heating plant. Okay. Now, question may come up about multiple curves. You know, why is a 20 or fewer apartment complex not equal to 130 or more apartments? The curves in there account for something called diversity, which really works into our favor when we start to get to larger units. Here's a little bit of explanation from a guy named Roy Hunter. The name will come up again when we talk about the modified Hunter's curve. But basically, when we look at diversity, it's all about probability. You know, if you read this, it says, assuming that there are n fixtures in a system, each operated once in t seconds on average, and that each operation is of t seconds average duration, what is the probability that k fixtures will be found operating simultaneously at any arbitrarily chosen instant in time? What it really comes down to is when we start to look at a lot of the methodologies, the more fixtures there are in the building, the lower the probability that a large number of them are going to be open, and I can use diversity to lower my my water heating plant. So you look here, you know, the curve that for 20 or fewer apartments per apartment is always going to come up with more recovery and more storage than any other curve there. So let's take a look at how to utilize this. So I have a 150 apartment unit. I tend to go in there looking at it from the aspect of storage. So I'm going to say I have 300 gallons of usable storage. Now remember, this is usable storage. What's the drawdown on your water heating tanks, water tanks? So, you know, 300 gallons of usable storage is probably actually 400 gallons of stored water. Okay. So I have 300 gallons, I have 150 apartments, I divide 300 by 150. That's telling me that my stored volume is at the rate of 2 gallons per apartment. I'm going to enter the bottom scale. You see that red line come on at 2 gallons per apartment. I'll follow that line up, and I have 130 or more apartments. So I look at where that line crosses my 130 or more apartments, and then I move to the left hand to my recovery. It's just about at 5. I like easy math, so I'm going to call it 5 gallons per hour per apartment. So I have 150 apartments. That means that I need to have a recovery rate of 750 gallons per hour. Yeah. If you change that over to heat input at 100-degree rise, I have to have 625,000 BTUs of energy going into my domestic hot water system. So one solution for this 150 apartment unit is 300 gallons of usable storage with 750 gallons per hour of recovery. Let's say I up my storage from 300 to 1,000. I now jump up to 1,000. 1,000 divided by 150 is 6.67. The green line that's going to come in right there, that represents my 6.67. I look at where it crosses my 130 or more curve. Let's call that 3.9. So if I multiply 3.9 by 150, I get 585 gallons per hour recovery. So right off the bat, just working off of this one curve, I now have essentially 2 options for water heating for my 150 unit apartment. I can either go at 300 gallons of usable hot water with 750 gallons of recovery, or I can go with 1,000 gallons of storage with 585 gallons per hour of recovery. So 2 data points, and you'll notice 2 different numbers. Let's look at a different method. This one here, a lot of times you'll hear referred to as the average hourly demand. Again, directly out of the ASHRAE manual. So with this, rather than just giving an arbitrary number or a historic number based on what an apartment should use, now we're going to look at fixtures in the building. And with this, it's going to be fixtures at gallons per water usage per hour. So there's a water usage associated where we're, based on the data that's been generated through, for instance, a basin sink. During a 1 hour period, the basin sink will use 2 gallons of hot water. Now, just as with the previous method, it's divided up into different applications. So my first column is apartment buildings. Then I have clubs, gymnasiums, hospitals, hotels, so forth and so on. So it's going to be based on the application. Now, for this to work, because there is a full listing of fixtures, this one here, I need to know the number of fixtures. Just saying we're sizing for a 150 unit apartment building doesn't give me any assistance in trying to come up with a solution. Okay. Couple of blocks on the bottom. Number 19, has something called demand factor. That's where diversity starts to come in. So this demand factor is going to take into account that I may have a total flow rate that if every fixture in the building is drawing water, this would be the rate at which I have to provide hot water. But because it's an apartment complex, my demand factor is 0.3, which means I can have a significantly low gallons per minute or gallons per hour rate and still keep up with the draw in the building. Now the number below there is a storage factor. So for an apartment building, my demand factor is 0.3. My storage factor is 1.25. What I actually do is after I calculate my demand with the demand factor, I then multiply that number for an apartment building by 1.25 to get the storage, the usable storage for my tank. So a little bit different method. You'll also notice, unlike the previous method, my demand factor is fixed for all sizes of apartment, regardless of whether it's 20 units or whether it's 150 units. This method will give me a much higher water heating plant than the previous method was. So let's apply our apartment building to this. So each apartment, 2 private labs, 2 showers, 1 kitchen sink, 1 dishwasher, 150 units. So if I do the math for my basins, I have 3,000 bathroom lab basin sinks at 2 gallons per hour, which is 600. 300 showers at 30 gallons per hour is 9,000 gallons. I go down the list there. The kitchen sinks add 1,500 gallons. The dishwasher adds 2,250 gallons. I add those all up, and I get a grand total of 13,350 gallons per hour. Now, I then get to apply the demand factors, because I'm not going to size for over 13,000. I'm going to size for 30% of that. So I multiply it by 0.3. My demand is 4,005 gallons per hour. That now becomes the number that I have to work as far as my recovery. I then have to size my storage, so I multiply that by my storage factor of 1.25. It's telling my storage has to be 5,000 gallons of hot water. I now have a third solution to my water heating problem. There's a fourth method. I should say a third method, because I've done one twice. This method is probably the most prevalent for sizing. This is my demand. This is a method that looks at the recovery or the demand of the system. This becomes the no storage number. This is strictly based on recovery. Additionally, I would say this is probably the most prevalent in the usage. This way here, whenever you do storage, there always is the time factor involved that once that tank's exhausted, I'm down to storage. I think a lot of times that's what drives the use of let's call it the fixture units and modified Hunter's curve. So with this, it's not really based on a set gallons per minute of flow. you have a fixture unit, and the fixture unit is a dimensionless unit. So if I look at the definition, it's a number on an arbitrarily chosen scale that expresses the load-producing effects on the system of different kinds of fixtures. So if I look at my highlighted apartment building, a private lavatory basin is 0.75 fixture units. If I go down further to the last on there, my shower is 1.5 fixture units. What that's really saying is if you look at the demand on the system, the load producing effects, the shower produces twice the effect as a basin sink would. So just like doing the average hourly demand, I need to know the number of fixtures, but instead of calculating a gallons per minute, what I'm going to do is I'm going to calculate a number of fixture units. What I'll do with those fixture units is I'll apply it to this modified Hunter's curve. Now, the modified Hunter's curve actually is not a single curve. It actually is a series of curves based on application. So if you look here, there's a curve A, now circled in red. That represents the relationship for restaurants between fixture units across the bottom axis versus gallons per minute on the vertical axis. The next one down is curve B, which includes hospitals, nursing homes, nurses' residence, dormitories, hotels, and motels. So a little bit lower effect for the number of fixture units. It'll end up with a different gallons per minute if it was the same number of fixture units. Curve C, there's my apartment houses. That's the one we're going to use in our calculation. And then curve D, office buildings, elementary and high schools. Now, with all these different curves, it's important to know your type of application because 1,000 fixture units can mean different things based on different applications. You look at where that 1,000 fixture unit line crosses the four curves. It could be 50 gallons a minute. It could be 75. It could be 107. It could be 210 gallons per minute, based on the application. So let's apply our apartment building. So we have 150 units with all our 2 to 3 bedroom house, and 2 to 3 bedrooms and 2 full baths in the apartments. So if I look at, again, going to the basin, for a private basin, the fixture unit is 0.75. That means my basin fixture units is going to be 225 with the 300 basin sinks. With the 300 showers that have a fixture of 1.5, that's an additional 450 fixture units. The kitchen sink comes in at 0.75. So with 150 kitchen sinks, there's 112.5. And then the dishwashers have a fixture unit of 1.5. There's 150 of them. That gives me an additional 225. So if I add it all up, my apartment building represents 1,012.5 fixture units. Now I can utilize that information with the modified Hunter's curve to get the gallons per minute flow rate that this demand represents. So I enter in the bottom at 1,012.5. I come up to curve C, which is apartments. I go over to the left-hand side to the vertical axis. And from that vertical axis, I get 75 gallons per minute. I'm looking at it from an hourly standpoint, that comes up to 4,500 gallons per hour. The heat source needed to generate that flow of water at 100-degree delta T is going to be 3,750,000 BTUs per hour. And this application doesn't require any storage. The water heating plant will keep up with the demand in the building. Now, for the next method, I actually want to show you one that also is available, soon to be available online as a website. This method is called the OT method. OT means occupational type. So with all of the other previous methods, everything looks at it from either the fixture or a set amount per apartment. The occupancy type looks at it also from the aspect of the occupants. So the occupants in the building, do they generate a low demand, a medium demand, or a high demand? Again, the easy ones in each one of them, a low demand, is it a couple? Medium, is it a family? High, is it a large family? Now, additionally, this methodology also doesn't just look at a peak period, it looks at a number of peak periods, in that you can take a look at sizing of the storage and sizing of the recovery to give me my best performance to cover all possible aspects. I'm actually going to click on the link on the bottom here and kind of jump over to a microsite that's out there that contains this methodology. So this happens to be our microsite. Here's the OT method here. This site's not available yet. It's still in development. But this is the OT method, and it looks at occupants, demographic classifications. And with this method, it's only used for apartment buildings. So if I scroll down, here I address my demand. Is it going to be low? Is it going to medium? Is it going to be high? Again, low, here's couples on here. There's also other things that represent a low demand demographic. If I go to medium, here's families, and then I got another couple of instances that represent a medium demand. If I go to high, I'll go down near the end of the bottom there, high number of children, a big family. Each one of these will give you a different number, and we'll actually look at doing our apartment building as a low and a high to kind of give you a feel for it. For the comparison, I'm going to stick with the low numbers when I start to look at comparing it to other sources. So if I click on low, then here I'm not going through the fixtures. I am actually going through the type of apartment it's going to be. So my apartments are all 3 and 4 bedrooms, as I identified. So I'm just going to put them, for the sake of speed, I'm just going to say, okay, actually they're all 2-bedroom apartments. Now, since this is a manufacturer, since this is our website, you know, we want to generate, it's going to generate not only information about the application, but it'll also drive it to product. I got to select a couple of things on here. And for a low demand application with 150 2-bedroom apartments, I need 17 gallons per minute of recovery, which will require 760,000 BTUs of input. Additionally, because of the water heater that I chose, it's going to select 4 of them, and in those 4 water heaters, I'm going to have about 440 gallons of usable hot water. So different method still comes up with a solution for an apartment building. Now, notice what happens to my recovery and my number of units if I go from a low demand to a high demand. My 17 gallons a minute jumped up to almost 64 gallons a minute. My load jumped up to 2,870,000 BTUs. My 4 tanks jumped up to 10. So with this method, and a lot of times this is probably one of the tougher informations to get for this, is you do need to know the occupancy type, because it will have a significant impact on what kind of water heating plant is necessary to keep up with it. But again, solid method, you know, it is used out there, and it's one that we will have available sometime in the near future as a water heating sizing methodology. So, where does this leave the designer or somebody that's helping somebody design a water heating system? If it's something that nobody's discussed beforehand, it could leave you with a wide variety of numbers. So I kind of put this together to look at the methodology that we talked about so far that's outlined in the ASHRAE. But then I also wanted to throw in some information based on sizing methods that various manufacturers utilize. So from the first method, where we did it in 2 different cases, I can meet my 150 apartment unit with 750 gallons of recovery with 300 gallons of storage. I can increase my storage to 1,000 gallons and then reduce my recovery to 585 gallons per hour. If I do average hourly demand, I'm up to 4,000 gallons per hour of recovery with 5,000 gallons of storage. The next one over, Hunter's curve. I'm looking at about 4,500 gallons per hour recovery with no storage. The OT method, occupancy type, 1,013 gallons per hour with 440 gallons of storage. My first manufacturer, this one actually was a calculation on a worksheet. This one here was 960 gallons per hour with about 400 gallons of storage. Manufacturer 2 was a software on the website, 912 gallons per hour with 166 gallons of storage. Manufacturer 3 was a different manufacturer, also web-based, 1,200 gallons per hour recovery with 257 gallons of storage. And then manufacturer 4, also web-based, 698 gallons per hour of recovery and 167 gallons of storage. So you notice the numbers, there's a pretty big diversity from the various methods. Again, you know, a lot of people go with the Hunter's curve, and we're going to check this in a couple of minutes, by the way, because it tends to be a very safe number. You know, it's on the higher side, and it's also a zero storage number, where I will always have the ability based on recovery to keep up with the domestic hot water demand. Now with that, I want to run a little bit of a poll here. So I've talked to you about the various methods. Now I'd like you to tell me which one of the methods you employ. Is it fixture units and Hunter's curve? Is it average hourly demand? Is it occupancy type? Do you rely on a water heater manufacturer, or do you have another method that you utilize? So we'll take a few seconds here, and we'll let the poll run, and let's see where everybody stands. How we doing, Miranda? Out of how many? What's that? Out of 14. All right, if you could weigh in there. Right now we have not very many of you have weighed in on the poll. Nine out of 4, okay, all right. We're about at 9 out of 14 have weighed in, so let's take a look, Miranda, see where we are. All right, and believe it or not, the numbers here look pretty close to the previous session that we've done. Overall, about 4 out of the 9 that responded all did fixture units. That was consistent with our previous group. The first group we did, fixture unit was definitely the big winner. We had one with the average hourly demand. I believe we only had one at the previous method as well. Water heater manufacturer, 4 out of 9. Again, actually the numbers were pretty consistent with what we had with the previous group. And then we also have 2 others. You know, and that one there, I was surprised in a couple of them that we didn't have any others, because I've seen quite a few applications where that is done. So if you want to close the poll out. Okay. Now that we've looked at how to size it, now let's take a look at the water heating methods. Okay. And when it comes to water heating methods, we really come down to, let's call it about 5 methods. 5 of them, 3 of the 5 are direct fired. 2 of the 5 are an indirect method, or a method using a heating system boiler. So there's a storage style where I have a flame built right into it down in the lower left-hand corner. If I work my way around clockwise, I also have storage in the indirect form. You know, a water heater that utilizes storage, but also a heating system boiler to generate the hot water. Next around is my tankless water heater, my zero storage or my on-demand water heating method. I also have, that's listed here as a direct fired boiler or a water heating boiler. That one you may also refer to as a volume water heater. That's a common term I've heard used for it as well. And then on the bottom is a plate heat exchanger skid system, another form of indirect that rather than using a tank uses plate heat exchangers or even shell and tube heat exchangers to generate the hot water. So we'll take a look at these 5 methods. And when we start to talk about it, what we'll also talk about them is in comparison. And I've kind of thrown up 4 areas of comparison that we're going to look at. These are the ones that tend to be in the discussion when anybody says, I'd like to take a look at water heating. By the way, you know, how do you stack up? Usually the stacking up questions are about initial cost, about footprint, about life cycle, and about operating costs. In reality, I could probably have put another dozen items up there, but we're going to stick with these 4 for our discussions. Also with these 4, I have to give the disclaimer on the bottom, and due to variation, this is not always cut and dry. You know, for instance, I could say that the initial cost, and I will say initial cost of a direct fired storage water heater is relatively speaking low. Then the question comes up about, well, what about if it's carrying an ASME stamp? If it's a big one with ASME stamp, it's like, okay, now we have to shift the discussion point. But again, these are kind of generalities when we look at the different methods of water heating. So let's start off with a traditional direct fired water heater. Traditional direct fired, we're talking about a tank of water with the heat source in it. Somewhere in that tank, we will have a flue, could be center, or could have a series of flues in there, and that's where the heat transfer happens. With this style of water heater, the water is in direct contact with a surface that is being heated by combustion gases, so it has a very high surface temperature, which will come into play in the efficiency and also in the longevity standpoint. Also, from a standpoint of setting it up, you know, I can go single or I can do multiple water heaters with these. And when I do these, it's usually a fairly simple install and control series. If I need more storage, I can also combine a storage tank with a direct fire to increase the storage volume, to increase my performance. And this is true for everything that has the tank involved. By having that volume of water, I don't really worry about minimum flow rates, which from an aspect of doing domestic hot water recirculation always makes some sort of storage tank in the system, whether it's direct fired or another form of storage tank, is a great option with recirculation. So how does it stack up? Well, this is kind of going to be my yardstick to measure against. Typically, storage water heaters are typically your lowest cost. The footprint also tends to be on the smaller side because the heating plant and the storage can be integrated into the single footprint. And most manufacturers also offer various combinations of storage versus a fire grade. You know, a lot of them, I can get a 200-gallon storage water heater with 200,000 BTU input, but they also have a 200-gallon water heater with 500,000 BTU input. So really, on the initial cost and the footprint is really where the storage water heater shines. As far as life cycle, having that heat transfer, having the direct contact between the water, the flue, and the combustion gases on the other side tends to keep the life cycle on the lower side. You know, the flue has to be light enough of material to give you good heat transfer. The problem is if there's minerals, particularly limescale in the water, now I start to worry about a buildup, thermal stress, and a loss of performance on that side. Additionally, from the operating costs, when you get to the larger sized water heaters, and if I'm doing a 500,000 BTU input storage water heater, it's probably non-condensing. So when I look at other methods that I can get into the condensing side of things, you know, there is an operating cost increase. The other thing with systems that have the flame, the heat of the system from the flame in direct contact through a heat exchanger to the water, you tend to have a quicker limescale buildup if hard water is in the area, which tends to drop the performance off much more dramatically when compared to indirect fired system. So overall, from an initial cost and a footprint standpoint, this becomes a great option. The next type is where I take the heat source and the storage and I separate them. So you'll hear them referred to as direct fired domestic hot water boilers. You may also hear this referred to as a volume water heater system. So I've now separated the heat source from the tank, but what also is, rather than having a lot of times a lighter constructed center flue, with this here, I'm often using the same heat exchanger design that I would in a boiler, so it tends to be a little bit more robust. So you do have a better performance as far as life cycle out of here. Now, by having the combination, it allows us to mix and match for a hot water need. So I can vary the tank size or I can vary the input based on what I want to do for my hot water demand. Additionally, what's nice is when I start to look at footprint, if I need to, I can do a pair or even 3 domestic hot water boilers with a single storage tank. So all of a sudden, there may be the opportunity in there to help minimize the footprint. Now, because the tank and the boiler the tank and the heat source are separate, I do need to pump the water between the two. So now the control of it becomes a little bit different, and there's a little bit more work involved to tie this system together. So, from an aspect of our 4 aspects, the initial cost, when I compare it to a storage water heater, it's going to be higher. You know, typically the boiler, because of the construction of the boiler, the hot water boiler, it does tend to push it up a bit. There is the material, there is the labor involved. However, when I start to look at redundancies, sometimes there is the ability to save some by going redundant on the hot water boiler and going with a single tank. So there's trade-offs that can be made. That also affects the footprint as well. Because the heat source and the storage are in 2 separate vessels, the footprint is going to be larger for the same amount of input and the same amount of storage. Again, when I start to look at designing, I may be able to go multiple boilers because all of these systems are going to have redundancy of some sort. I may be able to go redundant on the hot water boilers with a single tank and be able to give the redundancy that's needed and try and help save some on the footprint. From a life cycle standpoint, I'm going to call it medium. Anytime that I have raw water coming up across a heat exchanger with flame on the other side or combustion gases, the potential for a failure becomes more than separating it out and keeping the flame to water heat transfer in a closed loop system. But from an aspect of longevity, it certainly is going to be longer than a direct fired water heater. From an operating cost standpoint, you know, I see a lot of these going in with condensing direct fired, domestic hot water boilers. So if I can get into the condensing mode, I can start seeing good efficiency of it. So the operating cost is going to be lower. Again, depending on the water quality, you know, it may not be the best that you can see out there because of the fact that I will see buildup on there at a much higher rate than I would if I'm doing an indirect system. So again, great package for a lot of applications out there. The next method is the no storage method, the tankless water heater, the on-demand system. Okay, so what you'll see here is generally multiple on-demand water heaters packaged together to deliver domestic hot water with no storage. With this, it's all about recovery. So I have to size based on the load of the system. This is one that will have to be sized utilizing fixture units in the modified Hunter's curve. Without the storage, I can get to a fairly small footprint. And a lot of times with this, the footprint could be the width of the on-demand water heaters down the wall of the mechanical room. Okay. Now, because of the fact that it is all recovery, I have to make sure that everything is sized for that demand condition. Okay. So I have to go in there. There's no compromising by adding storage into it. The other thing with the on-demand system, there always has to be a little bit of thought going into the domestic hot water recirculation because I don't have that tank of water available. And the recirc may not be high enough to get the system to fire. So if I compare it, initial cost, a lot of times these are one of your more lower cost options. The footprint is small. The life cycle, I'm going to call it short, probably on comparison with the tank style water heater. And from an operating cost standpoint, a lot of it depends on whether they're condensing or non-condensing. And as the other methods discuss, it depends on how hard the water is. But there's a lot of variable in this, but this will not be your longest lived of your water heating methods. Now, the last two methods are both referred to as indirect methods. First one is indirect with a storage tank. So typically it's going to be a tank with a coil on the inside of it. A heating system boiler is going to be used as the heat source. And that boiler can be either standalone, providing domestic hot water only, or part of a combination where the heat source is for space heating and is for domestic hot water heating. Okay. Now, the thing I like about doing an indirect water heater or an indirect source water heating with both styles of it is I've now separated the heat source from the potable water. So Now the heat source will see a treated water that has low mineral content that I'm not going to have to worry about scale buildup because of minerals in the water over a long period of time. It's going to keep the efficiency up on that side of things. Additionally, because I'm generating the hot water with boiler water that may be 160, 180, maybe 190 degrees, at that lower surface temperature, the deposition rate of limescale on is significantly less. That way there, over the years, the rate of loss of performance is at a much lower rate than a direct fired method. The other thing that plays into it is because of that lower temperature, you tend not to see the limescale baking onto the heat exchanger. It's usually something that can be cleaned. And if the water heater has a clean out plug, as a maintenance step, it's easy to get in there and clean those heat exchangers down. So this one does bring a lot of positives into it. Okay. The negatives, well, let's look at our four methods. First one is the initial cost is going to be higher. Typically with this, when I do indirect water heaters, we're generally not talking about a water heater that I can transfer 500,000 BTUs. So for a commercial hot water plant, it's probably going to be a series of these, depending on it, 1, 2, 3, 4, or more to take care of the water heating needs. Because of that also, this method, you're going to end up with probably the larger footprint as well, looking at versus the other methodologies. Again, from a cost savings, if I do a combined boiler plant that takes care of space heating and domestic hot water, I probably can start to reduce the footprint because now I'm not having a separate heat source to drive the water heaters. That saves on cost, that also saves on footprint. And later on, we'll also look at a chart out of ASHRAE manual of how I can actually shrink the size of my overall heat plant as well. However, where the indirect systems shine is really on life cycle and operating costs. Because I'm tying it to a heating plant boiler, the expectation is that boiler should last at least 20, 25, 30 plus years. And because of the fact that I don't have any flame in this tank, I'm just heating with hot water, there's a lot less thermal stress and a lot less buildup of material on that coil, which will put the life cycle out much longer. Additionally, if this is coupled with a condensing boiler, I can also see significant cost savings from an operational cost standpoint. So when we look at the indirect methods, it's usually life cycle and operating costs become two of the bigger discussion points. I can do it with a storage tank. I can also do it with a heat exchanger. So I do a heat exchanger or heat exchangers coupled with a hydronic boiler. With this method, I can do it with or without storage tanks. So I have that level of adjustability. Okay. So the amount of hot water with this method as well as the tank, how much hot water I can generate or recover, it's really based on the heat exchanger's capability, but also the input of the boiler. Okay. And again, it can be a standalone system or it could be part of a heating plant. So where are the pluses and minuses? Initial cost, I'm going to put this on higher. Again, this is a variable number, and why I kind of go higher is in case I have to put couple a boiler with it, and I got to couple a storage tank. Those additions tends to push this method of water heating on the higher side. Footprint, I'm actually going in the opposite direction on this. On a small size, a lot of times this unit itself, you could probably get something that the footprint is less than 15 square feet. Again, if I start to look at adding storage into the system, then I have to account for the footprint of storage. If I'm going to do a standalone heat source, that has to be considered as well. And again, just as with domestic hot water with the tank style indirect, the life cycle is going to be long, the operating cost is going to be low. Now, I had mentioned this earlier. This is probably one of the biggest advantages you get when I do a combination or an indirect system that I can utilize a space heating boiler. Typically, when I look at the input for domestic hot water and space heating plus redundancy, I need to have enough energy when they're standing alone to cover the recovery for the demand. But when I do a combination system, I can apply a factor and downsize my heating plant. And this chart out of the ASHRAE manual really outlines the methodology of doing it. So to do this, I have to calculate a ratio. And the ratio is going to be the hot water heating load divided by the space heating load. And what I'll do is the bottom axis in here, that's the ratio. The vertical axis is the factor. The factor is applied to the domestic hot water load to calculate the additional energy needed to add to the space heating load. So for instance, if I have a building that the load in the building is 2 million BTUs, the domestic hot water load is 550,000, I divide my 550,000 by 2 million. That gives me a ratio of 0.275. So if I enter this chart at 0.275, I'm at about maybe 0.1 to 0.11. So that's my factor. So if I multiply 550,000 by 0.11, that's telling me that the number there is 60,500 BTUs per hour. That's my adder. So when I start to look at the size of the boiler, it's not that I need 2.5 million BTUs to take care of the entire load plus redundancy. I actually need 2,060,000. You may look at the way that the boiler size and the size of the boiler versus the actual load of the building. You may not have to upsize that 2 million BTU boiler to get there. You may have enough based on the way the firing rates of the boiler are spaced. So this can be a great way of reducing the heat source size if I'm doing that combination system. Now, with that being said, interested to find out, how do you guys approach doing domestic hot water? Really, when I look at doing the integrated heating plant for space heating and with domestic hot water. So how often do you integrate domestic hot water into the boiler plant for space heating? Whenever I can, sometimes or never. Let's see what we got for our results here. And whenever I can, 4 out of the 9, sometimes 5 of the 9, no nevers. That's excellent. And I would say sometimes is probably the biggest response we've got in the 3 classes we go. A couple of times we've had the nevers, and the never, a lot of times the never is about the performance of the condensing boiler. And that, you look at water heating and some of you say, well, I don't do a combination system because the boiler's not going to condense, because when I do domestic hot water, the water's going out at 180 degrees and coming back at 150. The boiler is going to run at 86% efficient. I can buy an 85% efficient water heater, just separate it out. So, I'm not going to go that route. Now, what we're going to do is we're going to look at a couple of things we can do if I do a combination plant to push the efficiency higher. Because with condensing boilers, it's all about dropping the return water temperature. And I'm going to try and, to keep us time on the shorter side, I'm really going to focus on 2 methods or 2 things that should be considered with the combination plant. Okay? Because with the combination plant, in most instances, the space heating is going to run off of outdoor reset control. So I'm going to try and drop my water temperatures to drive the efficiency. The problem is when I go to a domestic hot water generation period, the boiler has to come up to temperature to generate that hot water. Going out at 180, coming back at 150. As drawn here, the entire building gets 180 degree water. The end result is my condensing boiler is running at maybe 86 to 86.5% efficient. Okay. When I do a combination plant, what I would like to see and what I try and make sure is specified in there is a motorized mixing valve running out to the space heating side of the plant that will maintain the building on outdoor reset control regardless of what's happening on the boiler plant side of things. So let's say the hot water demand occurs, the boiler goes up to 180 degrees to provide domestic hot water, The water's coming back from my domestic hot water generating source at 150. With the motorized mixing valve, the requirement may only be for 120-degree water. So the water goes out at 120. Depending on my delta T's and how I'm running the VFD on the pump and everything else, let's say right now it's going out at 120, it's coming back at 110. In a lot of instances, the space heating load is dramatically higher than the domestic water heating load. So when you look at the blended temperature tends to lean closer to the space heating water temperature than the domestic water temperature. So let's say we're blending down that the return water temperature is 120 degrees. You know, at 120-degree return water temperature, I'm probably running at about 90% efficiency. So although I shouldn't be there based on where the boiler plant is running to support the domestic hot water, the mixing valve drives it to where it needs to be to maximize the performance. Now, the other method. We'll look at my fuzzy drawing. So here's another combination plant. This one has a series of boilers onto the left-hand side of the drawing. If you look at coming straight up at the top, there's going out to the space heating. And you'll notice my space heating is running on a motorized mixing valve as discussed in the previous slide, so I got that covered. Off to the left is a bank of indirect water heaters to generate domestic hot water. Yeah, black line coming over to the indirect water heaters, that's boiler water supply. Blue line coming back is my return. Now you'll notice, I'm going to blow it up. There's a small detail off to the right-hand side. And I'm going to identify that as a domestic hot water preheater. It's a plate heat exchanger. The plate heat exchanger is in the return line for the boiler water coming back and the supply line for the cold water coming in. So what we're going to do is we're going to take that boiler water that we pulled energy out inside the tank, and we're going to pull additional energy out as I preheat the incoming domestic water. All of a sudden, I've increased my delta T. So I may only have a 30 or 35-degree drop across the coil in the indirect water heater, but I may be able to pick up another 30 degrees across this plate heat exchanger. I go out at 120, I go out at 180 and come back at 120. I'm still in that 90% range for performance. So a lot of times when we look at these indirect systems and we're paying attention to overall performance, both from a water heating side plus a boiler performance side, the domestic hot water preheat becomes a great option on the domestic side. And it also helps us increase the overall recovery performance of the water heating plant as well. So, covered a lot of ground in the educational portion of it. So let's come back to the learning objectives to kind of recap what we covered and we're supposed to cover. So list the information required to size a water heating system, including the differences in the various methods. We went through that as we went through the individual methods. Explain how to size a domestic hot water heating system using the common methods. We went through those as well, the 4 methods that's outlined in the ASHRAE manual. We did a contrast of the various water heating methods, and then we described the ways of maximizing performance for an indirect water heating system and focusing on probably the 2 major impacts. Now, with that being said, I'm going to take a quick minute and take a look and see what we have for questions. Oh, we have a question. Okay. Question is from Steve. Is it not recommended to use 2 different sizing methods, then average them together to get a ballpark value? That's a good question. I guess most of that I've looked at have said that, you know, I would say the answer I typically get is I'm going to do the fixture unit and with the Hunter's curve, and that's pretty much it to cover the bases. But Steve, I'm going to have to take a little more research on that to find out, maybe a call around to a few people to see what they are doing. Thank you, Bakhtiar. You're the best. And with that, we'll close this window down. And let's talk about, now let's shift over to the commercial side of things. Talk about our new product, the Vitotrans 300. This is a skid-mounted domestic hot water generating package. Model designation is either going to be S3HA or D3HA. Big difference between the two. S is single wall construction, D is dual wall. That way there we have that dual wall hot water generation package to meet the needs required by code. From a performance number, the performance numbers don't suffer because of the dual wall heat exchanger. We increase the size so that each individual model that we offer gives you the exact same performance. So, kind of in a nutshell what we're providing. This is going to be a high volume domestic hot water production unit. We can get up to 180 gallons per minute hot water out of a single unit. It works with or without storage. It's available with either single or double wall, as I discussed on the previous slide. It will work with any hot water boiler plant. In reality, we should say any source of hot water. So if you have a source of hot water that can get it up, say, to maybe the 160, 180 degree range, there is the potential for generating hot water off of that source of hot water. Internally, it has a variable speed pump on the hydronic side. With that variable speed pump, we're going to utilize that to control the outlet water temperature. And by doing that also, it ensures that our water is running at the lowest flow rate, which will maximize the delta T, which will help with condensing boiler performance. Okay, 3 models are available: a Model 30, a Model 60, and a Model 90. The Model 30 has 1 heat exchanger and it has a single head variable speed pump. The 60 has 2 heat exchangers and that also has a single head variable speed pump. The Model 90 has 3 heat exchangers and this one has a dual head variable speed pump. Pump size, the pump is size that it will have enough residual head that this will be the pump that moves water between the heat source and through the unit. So no additional pump is required on the hydronic side of things. Okay, so internally, if I start to strip it down and take a look at it, we paid attention that it has to be moved around. So there's opening on all 4 sides to get a forklift in to move it around. If I want to crane it, we have the relief openings on the 4 corners of it to lift it with a crane. Okay, the footprint is small. It's about 14 square feet. Let's call it a little bit more than 6 feet long and a little bit more than 2 feet wide. Height-wise, again, a little bit more than 5 feet. We'll see the actual dimensions in a bit. It's modular in design for ease of service. So if I'm doing the 60 or the 90 that has multiple heat exchangers, there are isolation valves in there that I can isolate a heat exchanger, remove the heat exchanger and clean it without shutting the unit down. And again, internally it has a variable speed pump. And that variable speed pump is going to utilize its variable nature to drive the supply water temperature coming out of it. But by slowing the pump down, I'm going to change the rate of heat transfer, give me the best return water temperature. So if I'm connecting this to a condensing boiler, the condensing boiler will operate in condensing mode. Okay. Internally, if I have multiple heat exchangers, whether it's 2 or 3, there's no balancing valves in there. The manifolding is designed to be self-balancing. Additionally, to help keep the heat exchangers clean, there's a descaling pump in there. So when there's not a demand on the system, the descaling pump will come on and maintain flow through the heat exchanger so we don't have the sediment buildup in the heat exchangers. All of the domestic hot water piping is stainless steel. The base of the unit has an integral drip tray with a threaded opening. You know, that way there, when it comes to service, if I am pulling heat exchangers, the drip tray will gather the water up and, you know, I can put a hose on there to drain it directly to a drain without having to worry about making a mess in the boiler room. There is a Y strainer on both the hydronic side and the domestic side to help keep the Vitotrans clean. And all of the piping connections are off the back of the unit. All the panels come off readily, giving me ease of installation and also ease of servicing. Again, for actual dimensions, it's 26.5 inches wide, 73.75 inches deep, and 62.25 inch tall. Very compact, can fit it into a lot of locations. Okay. Application-wise, on the domestic hot water side, I can either apply it without storage or with storage. The logic in the control, if I need to do storage, does support a sensor going into the tank, and it also supports a domestic hot water loading pump to load the tank with domestic hot water. Additionally, show a recirc pump in there. The logic and the electric outputs for this will support the recirc pump as well. As far as the pumps and the connections, all of the internal connections are going to be 120 volts. For the pumps, they are going to be 2 amp. So depending on what you're using for a loading pump, this may be not actually a relay to bring the pump on, but more as an enable contact to a motor starter. Okay. One other thing I want to point out and kind of come back here, you'll notice if you look at the flow direction, this will come up in the discussion again, unlike volume water heaters, where it's set up that the pump comes on to push or move water through the volume water heater to recharge the tank. When the sensor in the tank recognizes that the temperature has dropped at the sensor, we want this system to respond faster. So cold water will always pass through the Vitotrans. That way there, the minute the draw gets above the minimum, and the minimum's adjustable anywhere from 5 to 30 gallons a minute, the minute I see the minimum draw on the system, the Vitotrans immediately starts to move, internal pumps come on, signals the boiler to come on to quickly start generating hot water without the lag that I may see if I'm just running off of the sensor in the tank. Sizing wise, our software package that I kind of previewed earlier, you'll have the ability to size for Vitotrans off of there. There's also sizing procedures within the Vitotrans Tech Data Manual if I know what gallons of flow I need and what kind of water temperature. So for instance, I can come in here with my flow and my water temperature, select my unit, select my operating temperature that I need for water coming in. Now, one thing that we currently aren't providing is a domestic hot water storage tank. That has to be field supplied. From a sizing application, depending on how you're sizing, if you're sizing Hunter's curve, modified Hunter's curve with fixture units, you're going to size the tank based on system reaction. How quickly can the boiler come on if the boiler is not hot already, and how long does it take that boiler to come up to temperature? If I'm doing any kind of domestic hot water sizing method, that part of the methodology is to size the tank, I may look at the reaction time and increase the size of the storage tank based on that reaction time if the boiler is not going to be maintained hot. And again, I mentioned this earlier, one of the things and one of our decisions in the design of the unit was from a piping aspect, let's bring all the water through the tank, through the Vitotrans, and by doing that, it will get the Vitotrans to respond faster than if we're simply relying on the sensor in the tank. That way, we can anticipate, get things up to temperature, and have a much more consistent delivery of domestic hot water. Piping-wise, the manuals do show a wide variety of piping, where I go in closely spaced tees, series in the system, or I can go a parallel install in the system, or if I'm doing something that requires primary, secondary, I'll bring it into the system after the primary, secondary connection. And for instance, here's a drawing that we had made up for one application, working left to right. There's my heating plant, my boiler to the side. This happens to be a Vitotrans CM2. In the center is my Vitotrans 300. And then I have a series of storage tanks to provide for domestic hot water. We can do it like this. We also have installations out there that have, proposals for installations out there that have no storage whatsoever. So there's a wide variety of applications and ways to apply this product. Okay. From a control standpoint, internally there's a PLC, very nice touch screen display on the front of it for display and also for input. We measure a lot of things internally. Pretty much every temperature that we would look at monitoring is there. So domestic hot water supply and return, boiler supply and return. We're also measuring flow rates for the hydronic water and also for the domestic water. All that shows up on the screen. When I select my methodology, if I'm going no storage, I'm going storage, the screen will reflect that, and also the settings that I need to will open up as well. And again, you know, when it's in operation, yeah, if we're recovering, you can quickly look at the screen, and the arrows do what you see here, indicating the recovery side of things. So you have your display, you have your inputs. There's also troubleshooting and, you know, a wide variety of things that you can program in the backside of the control. Now, from a control standpoint, internally, we do have set up an internal backnet network. Our network consists of the PLC. It consists of the programming unit on the front of the control, and it also includes the Grundfos Magna 3 pumps internal to the unit. Okay. Now, one thing you do have to recognize with this is the PLC can only host one IP address. And so if I am going to integrate this into a building management system, you will need some form of gateway to hook into the building management system, because otherwise, if I change the IP address on the PLC, I lose conductivity between the programming unit and the pumps. So just something to consider when I lock into a building management. But from a building management, the question did come up. Everything you see on the screen as far as temperatures and flow rates is accessible through the gateway. Okay, so what does the Vitotrans 300 represent? Well, it's a high volume domestic hot water package, and again, I can go up to 180 gallons per minute performance out of it. It does work with or without storage, and it will work on any source of hot water as long as the hot water is hot enough. Additionally, it's set up to run with or without storage. It has the input for a tank, and it also has the output for a loading pump and also a recirc pump if that's needed. And it's all, you know, when I start to look at the programming of it, that setup comes up readily when I make my choices of how I'm going to set it up. Additionally, this product is a product that's designed and built in North America. And that's the Vitotrans. So let's see if we got any more questions here. So a question came up. What is the reason to use bended corrugated pipes instead of direct smooth stainless steel between the manifold and the heat exchanger? Actually, I haven't talked to engineering about this, but I imagine it's about serviceability. You know, being able to get in there and readily take the unit out, take the heat exchangers out, and get them back in without having to worry about alignment. And the other question came up about the gateway. Currently, we're not providing a gateway, but I know our controls department is looking into it because it is needed. Oh, one came back up. So, covered a lot of ground today. First off, thank you all for participating in our webinar, and keep an eye out. I'm sure we'll be offering some more in the future. And with that, I'm going to turn it over. Do you have anything else to add, Miranda? And so Miranda I'm not sure if she has her speaker on, but just said look out for the email that's coming in with the information, and have a great day. Thank you.